Hi, everybody. Sorry, I'm like a minute late or two. My students, they just left the class, so. Okay, so we are gonna check out the lab today. Go ahead and download that. And then let me get to my file here and we will get started shortly. Okay, you can also open your IDE. You can use Visual Studio or Ripple. Okay. So let's share screen. Let me change the view real quick. Okay, so let's talk about graph in C++ today. And so to start, we're going to look at this graph. We have vertices 0, 1, 2, 3, and 4. So now what we're going to do is we are going to use this graph to identify the edges and the vertices and the adjacency list. Okay. So first we will start with vertices. 0, 1, 2, 3, 4. And that gives us 5. So for A, we just simply identify the vertices and then the edges. We have 0 to 1. And then 1 to 2. And then we have 2 to 3. And then we have 3 to 4. And then we have 4 to 0. And 4 to 1. Sorry, I'm missing one. 4 to 1. And we also have 3 to 1. As that would be an edge here. So once we have the edges identified, we can create the adjacency list. Okay. So we can say that 0 is adjacent to 1 and 4. Let me put that in purple. And then 1 is adjacent to 0, 4, and 2, and 3. So let's do it again, 2, 3, and 4. 2 is adjacent to 1 and 3. And then 3 is adjacent to 1, 2, and 4. And then lastly, 4 is adjacent to. And we would have 0, 1, and 3. Okay. So once we have the adjacency list for 1C, we can create the matrix, and you can use the bracket using insert equation, or we can just insert a table. Okay. We'll do a 6 by 6 table, and we can say vertex. And then we can say 0, 1, 2, 3, and 4. And then we repeat down here. And then we can start filling out our matrix. So 0 to 0, it's none because it cannot go to itself. 0 to 1, we have 1. Okay. Let me copy this. I'm going to move this down so we can see. Okay, and then let's do down. So 0 to 0 is none. 0 to 1 is 1. 0 to 2 is none. 0 to 3 is none. And 0 to 4 is 1. Okay, then we're going to go to 1. 1 to 0 is 1. Okay, 1 to 1 is none. It cannot go to itself. 1 to 2 is 1. 1 to 3 is 1. And 1 to 4 is 1. So the degree for vertex 1 is 4, as we can see. For vertex 2, 2 to 0 is none. 2 to 1 is 1. 2 to 2 is none. 2 to 3 is 1. And 2 to 4 is none. And we can repeat the same thing for vertex 3. 3 to 0 is none. 3 to 1, because there's no edge, right? 3 to 1 is 1. 3 to 2 is 1. 3 to 3 is none. And 3 to 4 is 1. And then we would repeat for 4. 4 to 0 is 1. 4 to 1 is 1. 4 to 2 is none. It does not directly connect. 4 to 3 is 1, and 4 to 4 is none. So this gives us the matrix for our graph. So before you start programming, if you're looking at the graph, you really have to look at what will be adjacent or the edges, right, with the vertices, and then also what will be the matrix, so you can build that out. Any question? Okay. So as you complete the matrix, that's part of 1C, we're going to take a look at your program. And while we wait, let me double check something real quick. Okay, so in this program, we're going to use vector. And it talks about vector using the pushback method or function, I should say. Pushback is used to add an element at the end of the vector. And if you're familiar with vector from like CIS17A, right? All that is going to add to the n element in that container. So it's going to add to the one at the last. So as it adds, that element becomes the last element in that container. So that means that it has to increase its size by 1. So whenever you do a pushback, right, the container, the vector is going to grow by 1 element as it adds in that element as the last. And what it will do is going to reallocate the storage space if and only if the new vector size surpasses the current vector capacity. So when it exceeds the capacity, then it's going to reallocate the memory location where that vector is stored. Okay, because it needs to expand that space to fit the vector. So now what we're going to do is we're going to take a look at the program. So as you are using vector, you need to include the STL. So we are going to include vector. And in this one, we are going to have a function, and this function is called add edge. Because remember that we are writing a program that's going to simulate a map or a graph. And so in the vector, since we're using vector and the element data type is going to be integer, so we need to make sure that we specify the type there. And we're going to use adjacency array or ADJ array. So that's going to be the argument. And we are going to use u and variable v. Okay. So this function is designed to add an edge to an undirected graph. So we have a vertex and we're going to add the edge to the vertex. Now we have a second function and we're not returning from a function, so therefore we're using void. In the second function, we're going to use it to print, to display. So now we're going to print the adjacency list. So again, we have a function, and in this function, we're going to call it print graph. And in its argument, we're going to have the vector, the adjacency list, and you're going to use the vertex, which is represented as variable v. So in this function, we're going to loop. So in our for loop, we're going to start with the first element, which is going to be 0. And it's going to go to the end. And we're going to increment up as we loop. So we're gonna display the string adjacency list of your vertex would be, and we're gonna bring down the value for the vertex as it loops. And in the nested for loop, we are going to have the auto X. And auto is the keyword, right? So it's then gonna go, it's gonna use the ADJ array of your vertices. And we're gonna print out what vertex is connecting to other vertex. And that will be representing as X. In the main, we are going to define what the capital V or the variable would be. That will be 5 to represent our graph, right? We have 5 vertices. And for our vector, we are gonna use the vector and we're gonna call, right, add edge function. In that, we need to specify which edges are established, as we had typed that out earlier, right? 0 to 1, 0 to 4, 1 to 2, and so on. So how can you know which edge is? You're going to look at the graph and you're going to specify the edge. Okay, 0, 1, 0, 4, 1, 2, 2, 1, 3, and so on. And then lastly, we're going to call the print graph function so we can display. So when you do this, it's going to draw the edges. And of course, it's not graphical user interface. We're just using text output to illustrate which edge is connecting. And then we're going to display. So when you run this, okay, first it's going to tell you the adjacency list of vertex 0. And 0 is going to connect, it's going to have an edge to 1 and 4. And then the second entry here, or the second things that it printed, was the adjacency list for vertex 1. 1 has an edge to 0 to 1 to 3 to 4. And how does it build this? It's really relying on the adjacency list to do that, right? And then on the third, it's going to display the adjacency list for vertex 2. And vertex 2, if you look at the graph, it's connecting to 1 and 3. And then next, that will be vertex 3. It has an edge to 1 and 2 and 4. And then lastly, adjacency list for vertex 4. 4 has an edge to 0, 1, and 3. So in this exercise, we see that we're using a vector. And we're going to push in, right, the values or what the vertex would be. And it's going to use that vertex array to be able to build out our adjacency list, which is then be printed. Okay. Any question? Okay. So what we wanted to go back is when we look at the adjacency list that we created for 1B, we wanted to see if it's going to match what's shown here. So is 0 have an edge to 1 and 4, right? That's verified. 1 is then adjacent to 0, 2, 3, and 4. 0, 2, 3, and 4. So it matched up. So manually, we had predicted that right? What will be the outcome of the program, and then we'll write that into the program. So then what you have is you would then verify. So we can say yes, right? It matches with exercise 1 because, right, the adjacency list that was created was incorporated by building out the edges in the main function here. Because this is what you say what would be the edges. So explain your answer. Then look at your code and look at the section that produces the adjacency list for the graph. Explain the functionality of the code and the overall program. So when we look at the program itself, right, we're going to focus on these two functions. First, the void edge or the void add edge, which allows us to build out the container that would represent your edges in the graph. And it's going to use that to be able to display your adjacency list. Because if there's an edge, that means that it's adjacent. And for question C, it asks you, given a graph, can a developer create a C++ program without evaluating the adjacency vertices? Not quite, right? Because we have to really examine the graph on how the vertices are adjacent to others to be able to incorporate the way that we approach this in this program. So without knowing the edges, you will not be able to establish the adjacency list. And having the edges, you would know what would be the adjacent. Question. So as you're looking at your projects from now on, right, if you choose to do the travel salesman or the solar salesman case, which is case 1, then you have to incorporate the weighted graphs to really determine, right, adjacency lists and so on. And then you also have to determine the shortest path and the cheapest path. Any question on exercise 1? Okay. So what we've learned from doing this outside of just programming our adjacency lists, we're also using vector STL, right? We learned how to write a function that incorporates vector, which is a data container. And we're using a function that's built into the vector STL, which is pushback. Now you can use array, but vector is more flexible in that it would grow and shrink as needed. So the size is adjustable based on the number of elements that you have. And it does have the capacity based on, right, the data type that you push or you store inside that container. Okay, any question? So the second part of the lab goes over data structure struct. In C++, data structure is a way that we can group up data elements under an identifier or a name. And in this group, we can have different data types. So the way the syntax is made is that you would have the keyword struct, and then you would put in the name. And for the struct members, we would need to include its type. It could be int and double. So we can have type 1 as int here and type 2 as double and type 3 as float, for example. So the type name is just going to give us the name of the struct or the structure, which represents its type. So if you name it product, like this example, you would, the name product is going to become the type, right, of that object. Okay. So we first need to declare the structure type. And in this example, we call it product. And it has two members, the weight and the price. And so if we are creating a program that's going to calculate, right, like generate a receipt for the purchase of the product, then the user or the cashier would need to enter the weight. That could come from an automatic scale, as what you see in sales terminal, and then the price. And we'll be able to calculate that. And as you see that under the struct, we would use different data type, int for weight, double for price. Yes, you can use double for weight, but what it's showing you is that you can use data type under the struct. It's a way that we can group it together. So then product will become the data type for apples, banana, melons, beans, rice, right? Oranges, so on. All the products that we might carry, like maybe at a food store. The produce, right? Okay, so that gives you an overview of what struct would be. And I know some of you learned this in CIS5 and 17A. Also, we're going to talk about class a little bit. So a class is a way that we can specify a form of an object that it combines data representation and methods for manipulating the data. So under the class, you always see member variable, which contains data. And you also see member methods or functions. Those members would then be used to be able to manipulate data in the case where that we would utilize an object of that class to be able to access the attributes of that data. So when we define a class, you want to use capital letter, like in this case, the example shows you here, we would say class box. And to access it openly, we would use public, or you can make it private where you don't want that to be accessible. Okay, so we would then define a class, And then you would indent in and we would say these are the member variables. So double length, double breadth, double height, those are the members variable that we can use to calculate the dimension of the box. So public would then allow us to access the attributes of the members. So if you want to set it private, then it becomes inaccessible to other members outside of the class. You can also set it protected. And this will be the same concept in Java as is in C++. Okay. So in a program, you can have many classes, and some class would be accessible to others and some classes not. If there's certain data that you don't want to have access, in the case if we're looking at things that more commonly used in the real world, like social security number, right? Then we don't want to be able to use that in other classes. So we would then make that protected or could be private. So in an application, you can have hierarchy in the class. You can have a superclass or a parent class, and then all the subclass underneath that. And the subclass would then inherit the characteristics of the super or the parent class. So in 17C, they should address on how to, and some of you have also learned this in 17A, right? So what this does is it kind of gives you the overview on what a class would look like and what's consisted in a class and how to define a class, because you're going to see it in the program. So in number 3, we're going to refer to the graph. And this is a directed graph. And we're going to first identify the vertices and the edge of the graph. So we can start with the vertices. Here we have 0, 1, 2, 3, 4, and 5. And then the edges. So we can start with 0. So 0 to 1. And then 1 to 2. And then 2 to 0. And then 3 to 2. And then we have 4 to 5 and 5 to 4. So unlike the undirected graph, what you see is the direction is important, because when you're looking at the direction, let's say from 1 to 2, oh, I forgot the 2 to 1. It is different than from 2 to 1. When I have 3 to 2, there's no 2 to 3, right? It's just 3 to 2. In an undirected graph, when the line is just a line, there's no arrow, then we can go both ways. But in a directed graph, what you see is that you cannot go both ways. It's only going to be one way. In the case it's both way, it's going to show two arrows. So the adjacency list, it will be also be different. So we'll start with 0. Zero is adjacent to 1. Can it be adjacent to 2? Anyone know? Then we have 1 is adjacent to 2. And then 2 is adjacent to 0 and 1. And then 3 is adjacent to 2. 4 is adjacent to 5, as 5 is adjacent to 4. Question? So now we can also build out the matrix. So we're going to go ahead and insert table. We're going to do a 7 by 7. And then the column oh, I forgot the 0, sorry. So we're going to go down. 0 to 0 is none. 0 to 1 is 1. 0 to 2 is none. 0 to 3 is none. 0 to 4 is none. 0 to 5 is none. Next is 1. 1 to 0, right? Remember, we're going from 1 to 0. There's no the other way. So 0, 1 to 1. 2 to 0 is going to be 1. So let me grab this. Okay, so 1 to 3 is none. 1 to 4 is none, and 1 to 5 is none. So 2 to 0 is 1. 2 to 1 is 1. 2 to 2 is 0. 2 to 3 is 0. 2 to 4 is 0, and 2 to 5 is none. For 3 to 0 is none. 3 to 1 is none. 3 to 2 is 1. 3 to 3 is none. 4 is none, and 3 to 5 is none. Then 4. 4 to 0 is nothing. 4 to 1 is none. 4 to 2 is none. 3 is none, 4 to 4 is none, and 4 to 5 is 1. And the same thing with 5 to 4. Question? So then after we have our matrix from the graph, then we're going to build our program. So in this, we're not using anything extra. So IO stream for C and C out using namespace std. There's no extra STL that we're going to bring in. We're going to have a structure called node. And in this, it's going to have a member called val. And since node is now the type, okay, we're going to point to the next node by using node next with the asterisk. Then we are going to define a structure called edge, and it's going to have two members, the source and the destination. Next, we're going to define a class called graph. And in this class, we are going to build out the node based on the adjacency. So recall that node is the data type, or the type, I should say. And we are going to use a function called get the adjacent list node. And we're going to, for the parameter, for the argument, we're going to use destination and the head. So now we are going to have a constructor. And the way that you define the constructor is to use the new keyword. It's going to construct an object of node called new node. And this object is going to be used. It's going to have the value, and that's going to store in destination. So remember, values the int, right? It's a variable that we declared previously in node. And we're going to point to the new node, which is the next node. And that's going to be stored in head. So abstract level, what we're doing is we're building a data structure, okay, that's going to represent each node, and each node is going to represent your vertex that's connecting to the edge, or what we would see as adjacency. And we're going to return from that function the new node. The n here is going to represent the number of nodes in the graph. Okay. Then what we're going to do is we are going to create or use the pointers to the node to represent the adjacency list. Then now we're going to have another constructor. Since we have a class graph up here, okay, that is going to be used here. So what we have is we have graph, and we're going to establish the edge. We're going to construct an object called head. And we're going to use the keyword this to say that it's going to point to n as n. Since we're using pointer, we have to declare what no pointer would be. So in the for loop, we're going to iterate from 0 to the n, which is n. And we're simply going to point because we're using the pointer. So here it talks about initializing the pointer head for all the vertices. Then next, we're going to have a for loop. And this is where we're going to draw the edges. Now, you don't have to use an unsigned like this, but unsigned just represents a positive value, right? We learned about that first week. So we're going to start with the first element and go to the end, which is n, lowercase. So to draw from one vertex to another, we would start with the source. And we're going to use the index for the edge. And then also your destination is defined as the edges for the destination. Now, here is where you are going to insert. So new node, and we're going to call, right, the function and its argument, destination and head source. And since you use the head source, we got to define what that is. So head source is going to be new node, which we constructed a while back. Okay, you don't have to add in these comments. But if you read that, it says when you uncomment it, you would be able to do something else with that. And as we have a constructor, we have to deconstruct. So we would then need to, when you use new, then you need to delete. So instead of delete them individually, we would loop it so we can delete it. Because C++ does not do garbage collection. So we have to clean it up. Then we have a function to print, and this is going to give us the adjacency, right? So in the void print list here, you are going to pass the no pointer. Okay, and we can say that while PTR is not no pointer, we're going to print out the value, right, as PTR. It's going to point to the value. And from that, we reassign PTR, and PTR is going to point to the next. So what's really happening is that we fully use the pointer, and what we have association of what is the node, which is going to represent your vertex, and how that's going to be connecting to the edge, which is also be pointed. Okay. And then in your main, you have to define your array of edges. And why am I not using int here is because remember that when you look at the top, struct edge was already defined. So we're going to use edge as a type. Okay. So here we would have type edge for the edges array. and then you would be able to put in your edges. Then we would declare what the number of vertices would be. That will be your big N, that will be 6. And then to calculate the number of edges for int N, we would do the size of edges divided by the size of edges with the first element. We have a struct up here for node, which we use. We have a struct for edge, and we have a class called graph. So down here in the main, right, you are going to construct the graph by using graph, because that's also a type. And then the parameter, you're going to do edges, and the argument is going to be edges and the big N, which represents the number of vertices. How are you going to draw the graph? You're going to need the edges and the vertices. So we would then have a for loop, start at the first element, go up to big N, which is 6. And then we're going to print out the index each time. And then lastly, we call on the function print list. Okay. And then we're going to print its neighbor vertices. So here we go. Okay. So throughout all of that, right, we are able to draw our graph 0 to 1, 1 to 2, 2 to 1, and 1 to 0, and so on. So this program, not only that we elevate it by using data structure, right? We are creating a data structure and abstract, and we use pointer to be pointing to the location of what would be representing our edges and our vertices. So if you're taking 17C or you've taken 17C, you should be able to read this program and understand exactly what it's doing. And if you haven't taken it, right, this is a good opportunity to further explore how to write a class, how to write a struct, how that can be applied to a C++ program to represent a graph. Sure, we can do a program with just 1 or 2 functions and then have a main and be done with, or we can elevate the program and efficiently use space or memory by using pointer and data structure. Okay, so run the program. And I copy and paste this so that way you don't have to type everything out because it is a little longer than usual. But if you do copy and paste it into your IDE, remember that Microsoft Word, right, it is another application compared to your IDE. So symbols might not interpret properly. Things like semicolon, quotation marks, you know, comma sometimes doesn't interpret as the symbols is, you know, it uses a different encoding. So therefore, if it throws an error that you copy and paste it in, possibly check the symbols, check those characters and fix them, retype them. So for A, it asks you to look at the program and determine the areas of the program that produce the representation of the graph components, vertices, edges, and adjacency. And if you read the comment, it tells you exactly where those are. right? We talked about the functions, how it's establishing the node and pointing to the next node. So you can summarize what those functions do, and also the class and how we're able to use the loop. Okay. Like this function right here to build the adjacency list. Like here, where you would construct the object and use the loop to be able to create your edges. Also here. Okay. So compare the program adjacency list to your result in exercise 3, question B. Is it the same or is it different? Right? So go back to what we typed out as the answer. Does it look the same or is it different? And again, we're going to have to answer, can you write a program without really determining which vertex is adjacent to others or the next? And then compare that to exercise 2. What areas of the exercise produce the edge directions? So how can we make it directed? Look at the program and tell me how you can represent the direction of that edge. Okay, and if you only review the comments, you would know where they are, and then read that section of code and interpret that. Any question? Okay, so make sure that we answer the questions. And I didn't ask for screen capture on this one, but if you do want to, you can provide it. That's fine. Okay, so to really accomplish the project, we have to really see how a weighted graph is done. Right? So far, we learned about a simple graph and we learn about a directed graph. But number 5 is going to give you a directed weighted graph, which represents, it's very similar to what we've seen in the project. But the difference is that the vertices are different, the weights are different, and so on, right? Okay, so for number 5, we are going to first, just like the other one, we're going to identify the vertices, which is 0, 1, 2, 3, 4, and 5. And then our edges. 0 to 1. And then we have 1 to 2. And we have 2 to 1, 2 to 0, and 2 to 1. And then we have 3 to 2. The same as the last one, right? We have 4 to 5. And 5 to 4. Then we can derive the adjacency list. So 0 is adjacent to 1, and 1 is adjacent to 2, and 2 is adjacent to 1 and 0, and then 3 is adjacent to 2, and 4 is adjacent to 5, as 5 is adjacent to, oops, 4. So after we write down our vertices, edges, and adjacency list, we can build our table again. But in the matrix in this one, we have to consider the weight. Okay. Oh, got the 0. Okay, so after we have the table, we would then go through. So 0 on 0, 0 to 1. We got to put 6 now because that's the weight for our edge. And then 0 to 2 is none. 3 is none. 4 is none. And 5 is none. And then we have 1 to 0 is 0. 1 to 1 is 0. 1 to 2 is 1 to 7. And then the rest is none. And then for 2, 2 to 0 is 5. 2 to 1 is 4. And then 2 to 2 is 0. And the rest is 0. And then we would continue with 3. 3 to 0 is none. 3 to 1 is none. 3 to 2 is 10. 3 to 4 is none. Or 3 to 3 is none. 3 to 4 is none. And 3 to 5 is none. 0 here, 0 here. 5, 4, and 5, they have edges. So 4 to 5 is 3. And 5 to 4 is 1. And 5 to 5 is none. Question? So after we have the edges and the adjacency list, we build out the matrix, in which, in this case, we put in the weight instead of ones. And remember that it is directed, so we're gonna follow the arrow. Then after that, we're gonna run the next program, which is very similar to your previous program, but there's some slight difference. So in this one, unlike the previous one, we have another variable under the node, the structure node here. We have costs. And this is gonna be where we're gonna put the weight. Additionally, we are in the edge, we're gonna have to put in the weight variable, because when we draw the edge, we have to represent what is the weight of the edge. Then subsequently, we would also have weight being defined as a new node that's pointed to cost. And mostly everything the same except for this section where we would then need to specify as we add the edges where it would be also have the weight attributes. So as it loop, it also draws, when it draws the directed graph, when it draws the edges, we want to also include the weight for the edge. And then as it insert, right, from top to bottom for each of the vertex, we also have an additional variable. As we specify at the top, we have to include that in the new node. Then the other parts are the same. Now in the main, we have a third value which represents our weight. Okay, so when you have the edges, not just from which vertex to which, you also specify the third value, which is your weight for each of the set. So when we run this, it simply gives us, right, the adjacency and its weight, the edges and its weight. Question? Okay, so after we have put the program into our IDE and run it, okay, You're gonna check your adjacency list to see if it's the same. It should be. And again, we're gonna answer, can you really build out the program not knowing which vertex is adjacent? So answer the question there. Now compared to exercise 4, what areas of your program that's going to produce the weighted edge? Okay. I just went over that. So when you take a look at the program, you need to take a look at how the variables are implemented to store the weight information and how it's used and how it's illustrated in the edges as the third parameter. So make sure that we answer these questions. They're pretty straightforward and simple. Identify the section of your code that would give you the weighted graph and explain the purpose of that section of the code, or sections, I should say. Okay. So now this only going to meet a fraction of your project, right? You have to really program what would be your shortest path and so on. So if you think about it, if you're looking at the lowest value in the low cost or the cheapest path, what you would need to do is you would need to look at how it goes from one hop to the next. Okay, so let me take you back to some example that the students have done so you can see. And I'm going to add the ones that was created last semester. Those are pretty good as well. So as you can see, the students that wrote this program, they had chosen to use the lab that you're doing, right, to really build that out. So you can definitely use a lab that you have learned to be able to implement for your project. And then additionally add on to it what will be the shortest path, what will be the adjacent path, and then the map matrix. Okay. So here it gives you the option on how you can take a look at, adjacency and so on. Okay. So what they did was they implemented. Now, can this program be improved? Definitely, you can. But as you can see, you can use the lab content and be able to expand on it and be able to use that for your project. Similarly with the other ones as well, right? Question. No question. Okay, so we only have to do 3 exercises for this week. Okay. For next week, to prepare for next week, we have a couple more. So For unit 11, we are going to go over chapter 5. So we're going to come back to chapter 5, which talks about cryptography. And for those of you who want to do Visioneer, this is the chapter to really look at, right? Chapter 5. And we are going to do a lab on Caesar cipher, which is one dimension less than Visioneer. But if you know how to do Caesar, you should be able to implement in Visioneer. And there are some examples out there, but don't copy people's code, right? You want to be able to achieve this. And so it's pretty fun to really do. So we would manually do to solve, to encrypt and decrypt. And then we would take a look at how we would be able to write it in C++. And Caesar cipher is just basically shifting. We're also going to cover modular arithmetic, how to work with mod or modulo, right? To do the calculations, like when you add, multiply, mod values, what would that look like? Okay. So make sure that we read chapter 5 going into unit 11. And then after that, we are going to do relations and automata. And you do have another quiz. Okay. So make sure that we don't forget to take the quiz this week and attempt the extra credit. Any questions? Okay. So I'm gonna stop recording.